In this video, we're going to learn to differentiate a new type of function, the so-called exponential function. So an exponential function is a function of the form f of x is equal to a times b to the x power, where a and b are constants, so they are fixed numbers in an actual problem, and specifically b is greater than 0. So notice b is what we would refer to as the base of that exponential expression. And notice that in a function of this form, the exponent is the variable. So that's what makes a function exponential versus perhaps polynomial, something like that. So we've looked at lots of functions that have exponents, but in the functions we've looked at, the exponent has been a fixed number and the base has been variable. Well, in an exponential function, the base, the big number, is going to be the fixed value, and the exponent is where we encounter the variable. So anytime we see something of this form where an exponent contains a variable, we're talking about something that is exponential in form. So we're going to focus on one particular exponential function, what we refer to as the natural exponential function, which is the function f of x is equal to e to the x power. Now e looks like a variable, but e is not a variable. E is what we refer to as a universal constant. So e is kind of like pi. E is just one of those numbers that is used so much that we happen to label it with a specific label. And when we see e in a problem, we know that e means something very specific. So e is not a variable. X, the exponent in this case, is our variable. So what is e? If e is something like pi, what is e? Well, e is an irrational number, but it is approximately 2.718. And of course, we can go from there. Fortunately, you have a button on your calculator that involves e. So where do you find that on your calculator? Well, if you look on the left-hand side of your graphing calculator, right above the LN button, which is right next to the 4, right above LN in blue, it's e to the x. So that will be the base e if you want to apply an exponent automatically. So if I want to access that value for e, I'm going to hit second and then LN, and then notice it brings up an e and it has a box for an exponent. So suppose I wanted e to the first power, which would just be e. I would then press enter, and there we go, we have e to the first power, so approximately 2.718. E is also in another location on the calculator, so if you find your division button, right above the division button, again in blue, you see an e. That e doesn't have an exponent though, so if we were to access e that way, it's just going to give us the number without an exponent. But again, we approximate that and we get the same value. So how you access e on your calculator is up to you. It's not going to matter which one you use, but in most cases when we encounter e is also going to have an exponent attached to it. So using the form that already has the exponent involved may save us a little bit of time. So I'll tend to use that particular form of that button e. Okay, so why do we care about e? Well, the number that we're calling e arrives in various applied contexts, including, and probably most importantly for our purposes, continuous compounding. So if we're talking about an account that is subject to interest, a financial account that is subject to interest, where interest is continuously compounded, that's one of the places where we encounter this value e. So the formula to calculate an account balance that is subject to continuous compounding is going to be a is equal to p times e to the rt power. So there's the e. So if we think of p as the principal, the starting value of an account, r as our interest rate, and t as the number of years that have elapsed, then approximating this value is going to give us the value of the account. Now keep in mind, anytime we use e, again, e is an irrational number. So anytime we plug e into the calculator, we're just getting an approximation. So anytime we're asked for an exact value related to e, we're going to leave it in terms of e. In other words, we get down as simple as we can and then we just leave the e alone. If we want an approximation, we're looking at an applied problem and we want just a rough approximation of the value we're looking at, that's when we'll use the calculator and we'll use those buttons for e. So e is special specifically because of what happens when we differentiate a function involving e. So what is the derivative of this function? Well, the derivative of the function f of x is equal to e to the x is calculated in the following way. So if we take the derivative with respect to x of the function e to the x, it turns out that the derivative is e to the x. That is going to be our derivative. Now, one important point worth noting, although the function has an exponent, although this function does have an exponent, the power rule does not apply. So in most situations we've looked at so far, as soon as we saw an exponent, immediately the thought is use the power rule. The power rule only applies when our exponent is a fixed number and the exponent is being applied to some variable base. In this case, when we're talking about an exponential function, again, the base is the fixed number and the variable is what's in the exponent. So the power rule doesn't actually apply to a function of this form. We have to use a separate rule. It has its own derivative rule, and this is the rule. So in other words, the natural exponential function is its own derivative. That is actually the reason it's called the natural exponential function. When we differentiate it, it is its own derivative. So taking the derivative of e to the x power, we get back e to the x power. It's its own derivative. So if we combine this, knowing what the derivative for this function is, with the other rules we already know, then we can also differentiate a bunch of new functions that involve this specific function, e to the x power. So let's try a few examples. So we want to differentiate each of the following. So our first function is going to be y is equal to 3 times e to the x power. So we want to calculate the derivative of y with respect to x. Now we know having a constant coefficient doesn't affect a derivative. Essentially, we can take the derivative of the actual function and then just multiply the coefficients separately. So essentially all we're differentiating here is the e to the x power. And we know if we differentiate e to the x power, it's its own derivative. So the derivative of this function is still going to be 3 times e to the x power. So let's look at one slightly more complicated. Now we have a product of two functions. So we'll think of this as x squared times e to the x power. In other words, one function where the power rule would apply, and then this exponential function where we use the rule specifically for that function. Now because we're looking at a bigger function that consists of a product, that's our indication that we need to use the product rule in order to differentiate. So just to recall, the product rule says we take the first function times the derivative of the second plus the second function times the derivative of the first. So the first function, x squared, times the derivative of the second function, well, the derivative of e to the x is just e to the x, plus the second function, e to the x, times the derivative of the first function, which in this case will be 2x. So let's clean that up a little bit. Now, in terms of hierarchy, in terms of the order we write things in, typically we write something that has a variable base before we write something that's exponential. So in terms of the ordering in which we would write things, in this case, for this first term, we'll just write it as x squared times e to the x. So the polynomial portion takes precedence, and then we write the exponential portion. And consequently, for this second term, we're going to rearrange things. So our coefficient will come first, and then the portion that's polynomial, and then e to the x. And it's not a bad habit to get into to factor something like this. If there is something that these two terms have in common, then we can factor that out. Will potentially be beneficial once we get to something that might involve the quotient rule. So what do these two terms have in common? Well, they have an e to the x in common, so that can be factored out. And notice we also have two x's here and then one x here, so they have one x in common, so that can be factored out as well. So I'm going to factor out an x, and then I'm going to factor out the e to the x as well. So that's going to leave me with a single x for my first term, and then from the second term, all I'm left with is the 2. So plus 2. So that's going to be our derivative. Okay, let's look at another example. So that would involve our product rule. Now let's look at an example where we might have to apply the quotient rule. And I know this is printed kind of small, but denominator is an x cubed. So we want to calculate the derivative of this function. Okay, so we have an upper function, we have a lower function. In this case, the quotient rule tells us we take the lower function, so low, times the derivative of the upper function. Well, our upper function is e to the x. We take its derivative, and we get e to the x. So low, d high, minus high, so the upper function, e to the x, d low, the derivative of the lower function, so 3x squared. All of that divided by the lower function squared. So x cubed squared. And then let's simplify that down. So again, in terms of precedence, we write anything that's polynomial first, followed by whatever is exponential. So that's going to be x cubed e to the x minus, rearrange, so coefficient, then x squared, then e to the x. And then in our denominator, we have a power raised to a power, so we multiply those exponents. So that's going to be x to the 6th power. Now, just like with the last example, we want to factor out whatever is common in the numerator. So in this case, both terms have an e to the x in common, and we also have an x squared in common. So the first term has an x cubed, the second term has an x squared, so they have x squared in common. So x squared and then e to the x can be factored out. So that's going to leave us with a single x from our first term, and then just the minus 3 from the second term. And then all of that is divided by x to the 6th. And notice in this case, the factorization is going to be beneficial. Now we have a factor of x squared in the numerator, and we have a factor of x to the 6th in the denominator. So we can reduce with what's in the denominator, cancel out 2 of the x's, which leaves us with an x to the 4th in the denominator. So our final function is going to be e to the x times x minus 3 divided by x to the 4th power. There we go. So we've looked at an example involving the product rule. We've looked at an example involving the quotient rule. What about the chain rule? Well, the chain rule is also going to apply to functions that contain e to the x, but this will allow us to differentiate functions where maybe there's more than just an x in the exponent. So what would something involving the chain rule look like if we're talking about something of the form e to the x? Well, this would be something where we have the base e, but our exponent is a function in x, not just x itself, but something else involving x. So something of that form is what we would differentiate now using the chain rule. So if we want to take the derivative with respect to x of something of this form, e raised to some functional power, not just x, but some function involving x, well, what does the chain rule tell us? It says take the derivative of the outer function with the inner function plugged in. Well, what would that look like for our exponential function? Well, remember, the derivative of our exponential function is itself. The derivative of e to the x is e to the x. So if we're differentiating the outer portion of this function, which is just e to some power, Well, it's its own derivative, so that's going to be e to whatever that power is. But the chain rule tells us we then have to multiply by the derivative of the inner function. And in this case, the inner function is contained within the exponent of our exponential. So we also have to multiply by the derivative of whatever happens to be on the inside. So in this case, f prime of x. So essentially, anytime we encounter a function e to some power, if we want to differentiate that function, it's going to be e to that power. It's its own derivative. And then we multiply by the derivative of whatever happens to be contained in the exponent. So let's try a few examples where we would need to use the chain rule. Okay, so our first example, y is equal to e to the 8x power. So kind of similar to this first function, but now instead of having a coefficient on e, we have a coefficient attached to x, which means that coefficient is now attached to the function that's inside of our natural exponential function. So let's take the derivative of this function using the chain rule. So we're going to differentiate the function as a whole, the outer function, e to some power, and we know the derivative of e to some power is e to that power. It's its own derivative, so e to that power. But then we also have to multiply by the derivative of the inside function, in this case, the function that is part of the exponent. So the derivative of 8x is going to be 8, so we have to multiply by 8. And then rearranging that, writing that in a better order, we have 8 times e to the 8x. Okay, let's look at another one. So e raised to this particular power, which is a quadratic trinomial. So e raised to the negative x squared plus 4x minus 7 power. So same approach, even though this exponent is more complicated, same approach. So the outer function is e to some power. So when we differentiate the outer function, we get e to that power. It's its own derivative. So e to the negative x squared plus 4x minus 7 power times the derivative of our inner function, in this case this function that is in our exponent. So if we differentiate, in that case we can just use the power rule and then the sum and the difference rule. So that's going to give us negative 2x plus 4. So now we just want to clean that up. So I'm going to write negative 2x plus 4 out front, and then I write my exponential after that. Now the only other thing that might be worth doing, notice we have a common factor involved inside parentheses, so we can also factor that. So I'm going to factor out a negative 2 from our parentheses, so that's going to leave me with an x, and then watch your sign for the next one. If we factor out a negative 2 from a positive, that leaves us with another negative. And then all of that is multiplied by e to our functional power. Oops, that should be a subtraction. There we go. Okay, let's try one more. So now we have a function inside of our exponential, but notice the function inside of the exponential would also be something that needs to be differentiated using the chain rule. So there are going to be a couple of layers to this last example. So the derivative of our function, we'll start with the outer function, which is e to some power. We differentiate e to a power and we get e to that power. So the first portion of our derivative, e to the square root of x squared minus 3. Okay, now we know we need to multiply by the derivative of that inner function. So normally when we have something with a square root, we rewrite it with a fractional exponent so that we can use the power rule, in this case the extended power rule or the chain rule. Okay, so we need to differentiate this inner function, this function, So remember, bring down the exponent. So that's going to give us 1/2 times x squared minus 3 to the negative 1/2. And then there's also a function contained within our inner function. So it's almost like 3 functions nested together. So I've differentiated the outer portion of this function, and now I need to multiply by the derivative of the inside, which would be 2x. Okay, so that is our derivative. Now we just need to clean this up. So first off, let's look at the coefficients. So notice we have a 1/2 and a 2. So 1/2 and then a 2, those are going to reduce to 1, so that goes away. Now, where is everything going to go in terms of what happens here? So notice with this negative exponent, automatically that creates a denominator for us. So this expression is going to go into a denominator. Now we also have an x, and we also have e to our functional power. Those two factors are going to stay in our numerator when we rearrange things and apply that negative exponent. So when I write everything in rational form, this is going to go to the denominator, so x squared minus 3 to the 1/2 in the denominator. And then in the numerator we have our x, and then we have our exponential. And remember, we're going to write the polynomial portion first, so x first, and then the exponential comes second. And so the only other thing we might want to do, normally we don't leave it with a fractional exponent when we can avoid that. And so in this case, we want to go ahead and write that back as a square root. So our denominator is going to be the square root of x squared minus 3. Now, don't make the mistake of thinking somehow these two things reduce to 1, cancel out. They don't cancel out. This is in the exponent for e. This is the power based on e. So in this case, this is not a factor that can just be canceled with the denominator. It's part of our exponential. So in this case, nothing reduces. That's going to be our final answer. So let's wrap up with an application. E is used a lot in real applications, so it's worth working an application. Okay, so more Americans than ever before are buying organic produce and products made with organic ingredients. The amount, A of T, in billions of dollars spent on organic food and beverages, T years after 1995. Okay, so that's given us the values for our variables. Our output is in billions of dollars. Our input is a number of years after 1995. This can be approximated by the following function. So A of T is equal to 2.43 times E, okay, so we know that now, 0.8 T power. So the first thing we want to do is estimate the amount that Americans spent on organic food and beverages in 2017. So notice this doesn't say anything about a rate of change. We're just estimating the amount, keyword total, we don't see that word, but the total amount that Americans spent on organic food and beverages in 2017. Well, this function tells us how to calculate that amount. What we need to determine though is what is T going to be. T is not going to be 2017, because how was T defined? T was defined as the number of years after 1995. So 2017 is how many years after 1995? Well, plug it into your calculator. So 2017 minus 1995, that's going to be 22 years. So 2017 is not going to be our input. T equals 22 is going to be our input, because T is the number of years after 1995. So let's evaluate this. So we want to know what was the amount spent in 2017, in other words, 22 years after 1995. So I'm going to sub that into my function. So 2.43 times e to the 0.18 times 22 power. Now, if you're careful, you can actually plug this into your calculator all in one line. You do have to be very careful though. So 2.43 times e to this power. So remember, e is right above the ln button in blue. So second, and ln is going to give me e. Now, depending on how new or how old your calculator is, your calculator may format it the way mine does, where it actually brings up an exponent. Or your calculator may format it just by typing e and then typing an up arrow. If it just types the up arrow, then you need to make sure you put everything in your exponent in parentheses in order to indicate that all of that is part of your exponent. Here, the way my calculator has done it, it's automatically formatted the exponent. So all I have to do is type in what's in the exponent, and it's understood that all of that is part of the exponent. So I'm going to type in my exponent, so 0.18 times 22, and then all of that is understood to be in the exponent. So there we go. So what does this actually mean, though, as an output? Well, remember, when we evaluate our function, a of t is in billions of dollars. So this is in billions of dollars. So we'll say approximately 127.5 billion. There we go, in total. Okay, next question. Estimate the rate at which spending on organic food and beverages is growing in 2018. So keyword here, rate. As soon as I see rate, think derivative, the instantaneous rate of change. How is spending changing at this particular period of time over that particular year? Well, in this case, we're talking about 2018, so that means t is equal to 23. And so we want to know, how is spending changing? What's the rate at which spending is changing when t is equal to 23? Well, if I want a rate of change, I know I need to find my derivative. So I want to find a prime of t. Now, be careful with this function. Don't become overwhelmed by the fact that we have numeric values that have decimals. This is just a coefficient for our exponential. So think of it as just being a coefficient, and we know having a coefficient does not affect how we take the derivative. So we just take the derivative of the function containing the variable and then multiply by our coefficient. So we're really just focused on differentiating this portion. So we have 2.43 times the derivative of our exponential function. So the outer function is going to be e raised to a power. So we know the derivative of e to a power is e to that power. So e to the 0.18 times t. But because we have a little bit more going on inside our exponent, we know we also have to multiply by the derivative of that inside function. So it's just power rule in that case. We have t to the first power, so bring down your exponent and then decrease it by 1. So that's just going to give us 0.18. So now we can multiply our constants together. So 2.43 times 0.18. That's going to give us 0.4374, and that is going to be our coefficient on e. There we go. So there's our derivative. So this is the formula for the rate of change of spending given a particular value of t. So in this case, we want to know the value when t is equal to 23. Okay, so I'm going to sub in 23 to the formula for my derivative. So 0.4374 times e raised to the 0.18 times 23. And again, I can just plug that directly into the calculator as long as I'm careful. So 0.4374, in other words, the answer on the previous line, times e to the 0.18 times 23. And notice 0.18 times 23, all of that is in the exponent. And so there we go. So what does this value represent? Well, we're looking at how spending is changing across a particular year. So the rate is billions of dollars per year. So this is going to be approximately 27.5 billion. And then since we're talking about a rate with respect to time, that's going to be per year. So that is going to be our rate of change as we go from 2018 and then onward. Okay, so this gives us a sense of how we calculate this particular kind of derivative. This is a very special derivative. Anytime we have an exponential function with a base of e, we always differentiate, and it is its own derivative. So we encounter something with a base of e quite often in different applications. This is just one example of an application where you might see something involving a base of e. So again, anytime we encounter something with a base of e and the variable is contained in our exponent, we know that function is its own derivative.